Review video number 8 is on exponents, roots, and exponential functions. First, we're going to start with looking at the exponent rules. Remember, anytime you're simplifying exponents, you can always come back to writing out what it actually means, whether it's repeated multiplication or division or anything, and then just simplifying by the basic rules of math that you know, meaning if there's the same thing on the top and the bottom of a fraction, you can simplify that to 1, or if you have 3 x's written out, that would be x cubed. But if you know the rules, then it would make your life a little bit easier. So we're just going to review these really quick. The product rule is x to the a times x to the b. So essentially, whenever you have the same base, you can add the exponents. So because the x is the same here, you would just add your exponents up top here. Okay. The power rule is anytime you have a base raised to an exponent and then that whole thing is raised to another exponent, you're going to multiply those. The quotient rule is if you have the same base on the top and the bottom of a fraction, so x here, you would then subtract the exponents. The negative exponent rule is if you have, anytime you have a negative exponent, you're going to flip it to the opposite side of a fraction. So for example, if it starts on the top, you're going to make it, because it's kind of like over 1, you'd flip it to the bottom and make it positive. If your negative exponent is in the bottom of a fraction, the denominator, you would flip it to the top and make it positive as well. And then the zero exponent rule is any variable raised to a 0 or any number raised to the 0 is always equal to 1. So now let's look at a couple of examples here of how you would use those rules to simplify. So this first equation, we have an exponential function, 20 times 6 raised to the 2x power. So using the power rule, we could separate this. And so we could rewrite that as 20 times 6 raised to the 2 times x. And again, rewrite that as 20 times 6 squared raised to the x. So we could rewrite the whole equation as y equals 20 times 36 to the x. So again, there we could use the power rule to simplify that problem. The next example, 1.750 times 0.75 raised to the 3x power. Again, we can use the power rule here. We can split this up. So we could write that as 1.75 times 0.75 to the 3 times x by the power rule, which is the same as 1.75 times 0.75 to the 3rd power, all raised to the x. And then again, if we're going to simplify that, we could do 1.75, and 0.75 raised to the 3rd power is 0.421875. And all of that would be raised to the x. So again, that's the power rule as well. So those are just 2 examples of how we could use that power rule to simplify our equations. Now we're going to talk about how to solve equations that either have exponents or roots on them. In class, we've talked about how exponents and square roots or cube roots are inverses of each other. So the inverse of squaring something is taking a square root, and the inverse of having a square root is using an exponent or squaring it. So what you're going to do when you solve these equations is just like when you're just solving for x, you want to isolate the variable. In this case, we're going to isolate our exponent or root using the properties of equality. And then you're going to do the inverse function to each side of the equation. So let's look at this first example on the left. We have 4x squared plus 3 is equal to 19. So our goal is to get this x squared alone. The squared only applies to the x because the 4 is not in parentheses. So we want to get the x squared alone. So right now it's being multiplied by 4 and then added to 3. So we're going to subtract 3 from both sides. We can keep our Grand Canyon line here to keep organized. We're left with 4x squared is equal to 16. Now the x squared is being multiplied by 4, so we're going to divide by 4 on both sides. We're left with x squared is equal to 4. Now you got to think about what's happening to x. X is being squared, so to undo that, we're going to use the inverse operation, which would be taking the square root. So we're going to take the square root of both sides. When we do that, the square root of x squared is just x. When you take the square root of 4, you get 2 answers, because positive 2 times positive 2 is 4, and negative 2 times negative 2 is 4. So the answer is plus or minus 2. So either positive 2 or negative 2, if you plug that back into your original equation, would satisfy this equation. So now let's look at this next example. We have the square root of 1 minus 5k plus 1 is equal to 5. So our goal is to get this square root alone. We want to isolate it. So right now, the whole square root is being added to 1. So our first step is going to be to subtract 1. So we're left with the square root of 1 minus 5k is equal to 4. Now everything that's left on that left side is all underneath that square root. So in order to undo that, the inverse of taking a square root is to square it. So we're going to square both sides. Remember, if you do something to one side, you have to do it on the other side. When we do that we get rid of that square root, so we're just left with what's underneath, or the radicand, which is 1 minus 5k is equal to 4 squared, which is 16. Now we can just continue like normal. We want to move the constant, so we're going to subtract 1 using the subtraction property of equality. We're left with negative 5k is equal to 15. K is being multiplied by negative 5, so we're going to divide by negative 5 on both sides. And so we're left with k is equal to negative 3. So if you plug that value, negative 3, back into your original equation, that would solve that equation. So again, with these equations, the biggest thing is you want to isolate that square term or isolate the square root term first before you go about doing the inverse operation. Okay, next we're going to talk about exponential functions. This is a huge topic and it's really important. Exponential functions always have a variable in the exponent. So it's not an x squared, it would be like having 2 to the x. The variable has to be in the exponent. A big thing about exponential functions, you can see it in the word exponent. Exponents have to do with multiplication. So exponential functions always change by multiplication and division. That is crucial that you know that and compare it to linear functions. Linear functions change by addition or subtraction. Exponential functions grow by multiplication or division. Their equations always look like this form. Y is equal to a times b to the x. In this equation, the a right here is your initial value, and the b is always your growth or decay factor. When you have exponential graphs, they're going to look kind of like a hockey stick shape. There's going to be a long flat part and then a dramatic curve upward, or it starts up high and gets lower and then flattens out. Either way, it's a dramatic curve and there's a long flat part. So when we're looking at this next example, we already have a table of points that are on that curve. And to prove that it's an exponential function, we need to prove that it changes by multiplication. So if we're looking at our y values, we want to see what is the change from 2 to 4. Well, 2 times 2 gets us 4. What about from 4 to 8? 4 times 2 gets us 8. 8 to 16, 8 times 2 is 16. So our growth factor, it's growing because you start with a lower number 2 and you get up to 16. Our growth factor, our b, is going to be 2. Now, in order to write an equation, we have our y equals, we need an a value. Our 2 is going to go here because that's our growth factor, and we know we're going to have a variable in the exponent. So now we need to find our a, which is our initial value. Initial values would always have an x value of 0, and so we need to figure out what number would we have here that when we multiply it by 2 would equal 2. So we need it to be able to times by 2. So if we put 1 there, 1 times 2 equals 2. So our initial value then is going to be 1. So if we were to write an exponential function that represents this set of data, or these set of points, it would be y equals 1 times 2 to the x. Now let's talk specifically about exponential growth and decay problems. These problems are super applicable in real life, and there's lots of them on the Regents exam. So you definitely want to make sure you're familiar with this. The setup of the formula is y is equal to a times 1 plus or minus r raised to the t. We already talked about how a is our initial value. Initial means starting, so it's whatever your current value is or whatever you start with. R is your rate, so by what rate is it growing, and t is your time. Now, to figure out if you should use the plus or the minus r depends on if it's a growth or a decay. If it's a growth, you're always going to want to do plus r, so 1 plus r would be your growth, and 1 minus r would be your decay. Because remember, when you're looking at these equations, if the b is greater than 1, that indicates it's a growth function. If it's less than 1, it's a decay. Some words that would indicate growth would be increase, raise, grow, appreciate, interest, double, or triple. Some words that would indicate decay would be decrease, decline, depreciate, lower, cut, fall. So in each problem, you really need to read through it and figure out what's happening here, and is the value growing or decaying, getting bigger or smaller over time. So now let's look at an example. The value of a car is $12,000 and is decreasing at a rate of 3.8% per year. Use an exponential function to find the value of a car after 4 years. So before we get started, we need to start by looking for some information. First, let's look for our initial value. Well, we know our initial value of our car was $12,000. Initial value is always A, so we can start by writing A is equal to $12,000. Next, we want to identify our rate. Our rate is 3.8%, so we can write that out. R is equal to 3.8%. We need to figure out if this problem is growing or decaying, increasing or decreasing. This word right here, decreasing, indicates to us that this is a decay problem. So I'm just going to write that down. That's really important for us to pay attention to. So now we have enough information to start trying to find our equation. So we know it's going to be y is equal to our initial value, and then we need to figure out what our factor is, and we're going to raise that to the t. So we're going to use this rate here, but we can't put percent into our equation. We need to change that to a decimal. So you go left 2 spots, so 0.038. Now we need to figure out, okay, if it's a decay problem, we need to start at 1, and we're going to subtract that 0.038, which comes out to be 0.962. So our equation is y is equal to 12,000 times 0.962, all raised to the t. Again, if this was a growth problem, instead of doing 1 minus 0.038, we would have done 1 plus 0.038. Now we need to look at the time. The question is actually asking for 4 years. So instead of just writing t, we're going to plug in 4 for that. So we have y is equal to 12,000 times 0.962 raised to the 4th power. When we plug that into our calculator, you end up getting 10,277.36. Whenever you are solving an exponential function, when you finish, you always want to think about what is the question actually asking. This is asking about a value of a car, which is money, and so your final answer, not only should it be rounded to 2 decimal spots, because money uses 2 decimal spots, or to the hundredths, you want to make sure you label it with your dollar sign. So the final answer here is $10,277.36. So that's everything for exponential functions and exponents. Again, some of the biggest things here is really exponential functions and exponential growth. You really want to practice these and pay attention and make sure you know these equations. You want to make sure you know what these look like. All of this is really important. You need to be able to identify if a function is linear or exponential, and you really need to know those inside and out. So make sure you spend a lot of time on this chapter. It's really important.